This video, we are going to discuss the introductory of another approach of modeling, which I guess you have heard this many times, which we call it as a neural network. I will split this topic into few videos. In this video, I will just discuss the introductory part of neural network. Let's start by recalling the discussion on linear regression. So we have this discussion in our previous videos. So let's say we have a collection of a paired sample data X and Y, and then we want to develop a linear equation to best represent the connection, the relationship between these two sample data X and Y. If we want to regress it with a linear line, so basically what we have to do, we have to find a line where the error between the data and the output represented by the regression line is the minimum. So if we are going to regress it with a linear line, as you can see in this slide, y equal to a0 plus a1x, then a0 basically is the y-intercept and a1 is the linear relationship between the input, output x and y. We discussed already on how to evaluate a0 and a1 in the linear regression discussion. And then if we want to extend it even further, we can also extend it to multi-linear regression. We discussed this also in that video. So extending it from a collection of a pair of sample data X and Y, we might have a set of input X, X1, X2, X3 until Xn and output Y. And we can also find the linear relationship between these X's, X1 until Xn to the Y as a linear function, like you can see in this slide. And basically, the model here is nothing more than the higher dimensional form of linear line. If it is in a two-dimensional form, in three-dimensional form, where let's say you have two input x1 and x2 and you have one output y, then instead of having a line, you will have a plane, right, to correlate x1, x2 to y. If you have more than two input variables, so you have x1, x2, x3, x4 until xn probably, then basically you can see it as a hyperplane, a plane in higher dimensional form, right? But how to find the relationship of this function is, we have already discussed it in the regression topic last time. We can also extend it even further, more than just a linear function. We can also have a polynomial expression, polynomial function that correlate the input x more than x1 probably to y, or we can also have a nonlinear function to represent the relationship between input and output here. You can do it with a regression approach as long as you can represent the function in linear form, right? Now, I want to view this linear regression problem from different perspective. Let us consider again a regression problem, but now we have two input, x1 and x2. So we have to input x1, x2, and we have the output is t. The output is t. We have two input, x1 and x2. So like just what we have already discussed in the previous slide. Then now you have three-dimensional problem here. The regression, you will have a plane as your regression function instead of a line. Then you will have a plane now. So you have a set of data x1, x2, and the output is t. We want to represent the relationship of x1, x2 to the t by constructing a plane equation y equal to a constant plus a linear combination of x1 and x2. So basically, this is just a plane equation like in our two variable linear regression, right? It's the same thing. So if we have a perfect model, if we have a very good model, then the error between y and t, the difference between t and y will be minimal, right? Because y tries to uh, capture the output t in here. If the model is perfect, then y should be equal to t, or at least y should be as close as possible to t. Okay, but now that's not my point. I want to represent this equation, just simple linear regression model here in a pictorial form. So I will write it. I will represent this function in pictorial form like this. I have to input x1, x2, right? And each of these input has its own weightage. So the weightage of x1 is w1, the weightage of x2 is w2, and I also have constant with the weightage of w0. So how to read this pictorial diagram is that just simply y is equal to w0 times 1 plus x1 times w1 plus x2 times w2. Okay, so basically this network, now let me call it as a network. This network basically is a multivariable linear regression model of y. Okay, for a single input variable, the network will be like just simply like this. I only have one input. I have one line here, one input, additional input, which basically for single input variable, this represent the y-intercept, right? So how to read this network? Just simply y is equal to w0 plus x times w1. And then I can capture any linear regression problem with this network, because this basically is representing this red line. To allow more flexibility in my network here, in my model here, I will now introduce one nonlinear element. This linear element can be anything. So I will re-engineer. I introduce slight improvement to my network here by introducing a nonlinear element here. The nonlinear element here can be anything, any nonlinear function. But let's take one most common case. I will use a sigmoid function, where sigmoid function looks like this. And then I put this as the nonlinear element to this network. So my complete network now it's becoming like this. How to read this network then? Y basically is just the function of A for Z, which appears as a linear function of x times w1 plus w0. So basically then here y is equal to function of A for w0 plus w1 times x, right? So therefore, y basically I just substitute this w0 plus w1x to this function, and then I will get the y. Okay, this is just nothing more. It's just a improvement that I made to this linear network. So if let's say to the same network, This basically is the to represent the sigmoid function that you have seen in the previous slide. If the W naught is equal to A minus 4 and the W1 is B 0.8, then the Y basically will be like this, right? This is the sigmoid function where the Z here is 0.8 x minus 4. Yeah? So if I plot Y as a function of x, it will be like this. It will look like that. It's a sigmoid function. Then you might have a question: why do we choose a sigmoid? Why do we choose nonlinear? Why do we choose to add a nonlinear element in our network? And in particular, why do I choose sigmoid function as the nonlinear element in the first place here? The first reason it is because it allows nonlinear flexibility to my data capturing capability. So instead of capturing a linear function, I can also extend it to nonlinear function. So it makes my model more flexible to capture not only linear function, but I can also capture nonlinear function. But so that is the first reason I can extend the flexibility of my network to capture nonlinear relationship. That is one reason. But the other reason is, yeah, I choose sigmoid because up to certain degrees, it still can capture linear model. If I have data here, a pair of sample data, which has a linear relationship between y and x, I can in such a way choose the parameters of the sigmoid, choose the parameters of W1 and W naught in that case, in such a way that this data falls in the linear part of my sigmoid data of my sigmoid function. So I still can capture a linear data up to a certain degrees, but at the same time, I introduce nonlinear flexibility in my network. So that's nice, right? So that's a, a, a smart idea to improve my network, improve my regression network. I will not call it regression anymore. This is my new network now, new model, new network. Wow, this is a nice thing also by allowing a sigmoid function to interact with my network. What? Let's take a look of this network. Now I extend my network instead of only having one network like what you saw in the previous slide. Now I combine two networks. I have two networks, so I have one input, two output, same like before, but then instead of using one network, now I put two networks in parallel like this with different weightage. So the W naught are different, the W1 are also different. So with this arrangement with certain weightages, I can have another shape of function. So I can have another shape here, which is something that I will not be able to capture it with just a simple linear regression function. Interesting, isn't it? So again, then that linear network that we discussed previously, after I introduce a nonlinear element and I use this network uh, together with other similar network, if I combine same networks with different weightages, if I combine them all, I can even improve the flexibility of this modeling to capture more and more nonlinear function. Even more, if I put 4 networks here, I can capture more complexity in my function, in my model, in my data, right? So here in this slide, you can see I have a set of variables, a pair of samples X and Y, and then I use 4 networks here with, of course, with different weightages for each of them. And then by using this, I can even capture more complex relationship between Y and X. So I introduce more flexibility in my model in that way, right? This what I indicated by red balloon here basically is the individual network that we discussed before. Now, what does it mean? How this will offer us in a better modeling approach? Let's say if these red nodes, each of these red nodes represent the a network, the single network that we discussed before. Basically, then by putting more and more and more networks into our modeling, intuitively, we should be able to capture any function, any form of function, even a complex function like this, you should be able to capture it with a collection of that networks. Let's say just an illustration. This part, I can approximate it by one network with one sigmoid function. And this part, probably I can also approximate it with another network, and the other parts I can approximate it with different networks. And then at the end, if we have a complete networks, I can capture this function with just a combination of these simple networks with nonlinear element. Okay, so this is the basic idea of neural networks, a combination of simple linear regression with nonlinear element, and we combine them all with different weightages. You should be able to, by doing so, we can improve the flexibility of the model to capture any type of function or signals or model, anything that you want to capture. Okay, so that is just a brief introduction on neural network, how and why we use neural network to model any function. Okay, in the next video later, then we will discuss in more detail how to construct this network for different types of data.